All right, well, why don't we go ahead and get started, and other people can join us a little bit later if they'd like. Welcome, everyone. My name is Chris Goforth. I'm the head of citizen science at the North Carolina Museum of Natural Sciences, and I am very excited to be hosting this live chat with a scientist. Today, we have a really amazing scientist for Astronomy Days, Dr. Patrick Treuthardt. He is an astronomer at the museum and does some really, really cool research and has a citizen science project. And so the way we're going to work this today is he's going to give you a little presentation, brief presentation, and then we're going to open it up for questions. So if you have questions that you'd like to ask Dr. Treuthardt, please feel free to type them in the chat. And we'll have an opportunity for you later to unmute yourself and ask your questions directly. But we'll do a quick presentation and then jump into Q&A.
All right.
All right, take it away.
All right, well, thanks. So let's see, we'll share screen. Let's do this. All right, so you're seeing the title slide then, right?
Yep.
Okay, excellent. All right, so yeah, so my name is Patrick Treuthardt. I am the assistant head of the Astronomy and Astrophysics Lab at the museum. And I'm going to talk to you about a citizen science project that myself and some collaborators put together. And so what I'm interested in is spiral galaxies. I'm interested in something called galaxy morphology and dynamics. So what that means is I'm interested in studying the shapes of galaxies and what those shapes can tell us about the underlying physics and the motions and the dynamics that go on that create those shapes that we see. And so, one thing I'm really interested in is a type of galaxy called spiral galaxies, and this is a project that we developed to get people involved in some actual research. So let me start out by showing you this image here. So a colleague of mine, Ian Hewitt, is actually going to be talking more about this, but I'm just going to give you a very brief overview of what this is. So this is something called the Hubble Extreme Deep Field, and this is a photograph taken by the Hubble Space Telescope of an apparently blank section of sky. And so what they did was they basically pointed the Hubble Space Telescope at a region in the sky where there weren't any obvious foreground stars, stars within our own galaxy or anything like that. And they just opened up the shutter on the Hubble Space Telescope and just, let the light come in. And they just exposed for a long period of time this really small region in the sky, and just to see what was there. So it's basically basically just exploration at this point. And so to give you a sense of how big this field of view is, if you take your arm and you extend it at arm's length, you close one eye and you look at your pinky takes up about 1 degree in your field of view. So the full moon, if you go out and you see the full moon, that takes up about 1/2 degree in your field of view. So if you do this, if you extend your arm, look at your pinky with one eye, you can actually cover up the full moon with your pinky. So that's about 1 degree in your field of view. This image is actually 1/25 of a degree. So what you're seeing in this image is what was seen in a very, very small section of sky. And everything that you see in this image, every little speck of light that you see in here is a galaxy in its own right. So our own Milky Way is a galaxy. It has about 2 to 300 billion stars in it. And so if we assume that all of these are about the same size as the Milky Way, you're looking at about 10,000 galaxies, each with about 2 to 300 billion stars in them. And in a section of sky where we thought there was really nothing there. We didn't know what was there. And so we just opened up the shutter and looked, and this is what we saw. So really everything that you see in here is a galaxy. So these little points of light that you see here and here, these little dots all over the place are galaxies. The only thing that aren't galaxies are, for instance, this right here and this right here. Those are stars within our own galaxy, and they're much closer, so they're much brighter, and that's why you get these diffraction spikes that you see here. So now if we kind of extrapolate that, if we take this image and we say, okay, so what does this mean for the rest of the sky? So if we kind of project outward, we can estimate that there are 2 to 300 billion galaxies in the observable universe. Now, there's some debate about that number. There was an estimate that actually went 10 times that, so about 2 trillion galaxies. Now there's new evidence to suggest that maybe it is actually more closer to 2 or 300 billion. But in either case, it's just a tremendous amount of galaxies in the nearby universe. It's remarkable. And so when we look out at all these galaxies, we see that there are really 2 main types. There are a type of galaxy called an elliptical galaxy and a type called a spiral galaxy. So an example of an elliptical galaxy is this thing here on the left. It's basically featureless. There's not a whole lot to it. You can see that it looks kind of yellowish. It's just bright in the center, and the brightness just kind of fades out. And what you're looking at is just old stars just being scattered around a common center. So if you could imagine taking that galaxy, holding it in your hands and rotating it around, there's no real structure, there's no real features to it. So any which way you rotate it, it's going to look pretty much the same. So there's not a lot of interesting things going on with this type of galaxy. So the galaxies I'm really interested in are these spiral galaxies, and these are 2 examples here on the right side. So this is a face-on spiral galaxy, and this is an almost edge-on spiral galaxy. So you can see that these objects are very, very thin. So if you imagine taking 2 DVDs and stacking them on top of each other, that basically gives you an idea of the ratio of thickness to diameter that a spiral galaxy is. So they're very, very thin objects, but they're very, very wide. And you can see that everything in the spiral galaxy is confined to a single plane. So here, when you look at it face on, you can see a lot of structure. You can see all the spiral arms. You can see these dark bands in here. That's dust blocking out starlight. And then if you look at it edge on, you can see all that dust being contained in the plane of the galaxy right here, in the disk of the galaxy. And this little thing that you see here, this is actually the bulge of the galaxy. So this is basically this region right here. So that's kind of puffed up, but the rest of it is all pretty much in a single plane. So in the 1920s, a scientist named Edwin Hubble, who he named the Hubble telescope after, he essentially created just the first real classification system for galaxies. And so he took those 2 main types of galaxies and he created a classification scheme for them. And we call this the Hubble tuning fork diagram. And so here on the stem region of the tuning fork, you can see we have different types of ellipticals. And then here in the tines, in the actual fork portion of the tuning fork, you can see that we have spirals. But you can see there are 2 different types of spirals. There are, along the top part here, we have what's known as non-barred spiral galaxies. And then here at the bottom, we have something called barred spiral galaxies. And the only difference is that these barred spiral galaxies have a linear feature running through the bulge of the galaxy. And then the arms come off the ends of this linear feature. But one thing you'll notice, the way he classified these galaxies, you'll notice that there are patterns to how they're classified. So for instance, if we look at these barred spiral galaxies, you can see that near the vertex, near this conjunction right here in the tuning fork, you can see that the bulges are very big. And then as you get further away, the bulges get smaller. And it's the same thing when you look at the upper tine up here. And you can also see that if the bulges are big, the arms are really tightly wrapped. And as you move further away from there, you can see that they actually get more open. So what we're seeing is we have galaxies where the bigger the bulge, the more tightly wrapped the arms are, the smaller the bulge, the more open the arms are. And that seems to be a pattern that we see in both barred and non-barred spiral galaxies. So one thing that we've seen, I'm sorry if this video is kind of jumpy. It's a little jumpy on my end. But one thing that we've seen, over time is that whenever we look in the center of any galaxy, whether it's elliptical or spiral, we find that in the centers of all these galaxies, in the nucleus, so in the very center of these bulges of galaxies, we find that every galaxy seems to have a supermassive black hole. And what that is, that's a black hole that's millions to billions of times the mass of the sun. So our own Milky Way has a supermassive black hole in the nucleus, in the dead center of the bulge of the galaxy. And so the animation that you're seeing on the left is a simulation of stars orbiting around an unseen object. And on the right, this is actual images. These are actual images put together to make an animated GIF of stars that have been observed over a period of years orbiting around an unseen object. And so what we can do is by looking at the orbits of each star, we can trace their orbit, and basically from each orbit we can measure the amount of mass that the star is orbiting around. So with one star, we can get an estimate of the mass that it's orbiting around. So if we do that with multiple stars, we have multiple independent measurements of the mass that's the star is orbiting around. And based on these orbits, we've determined, or not we, but other astronomers have determined that the mass that these stars are orbiting around is about 4 million times the mass of the sun, and it's contained in such a small volume that the only thing it can be is a black hole. And so obviously here you can't even see an object that these stars are orbiting around, and this is actually the black hole that they're orbiting around in the center of our own galaxy. That's about 4 million times the mass of the sun. So when we look at other galaxies, we see, similar evidence for supermassive black holes in the centers of other galaxies. And so this image here on the right, this is really the first direct image of a supermassive black hole in the center of a galaxy. So this is not our galaxy. This is actually in an elliptical galaxy outside of our own. And what you're seeing here is this orange kind of disk that you're seeing here with a hole in it. This orange disk is what's known as an accretion disk, and what that is, that's just a disk of material that's spiraling into a black hole. It's falling into a black hole, so it's spiraling down onto a black hole. And as it spirals down, it basically heats up and it starts to glow, and that's why you can see it. But that depression that you see here, that hole, this is where the supermassive black hole is. That's right in there. And this is the best image that we have. Best direct image that we have of a supermassive black hole, and that was made by the Event Horizon Telescope collaboration not too long ago. So the interesting thing is why does every galaxy seem to have a supermassive black hole? And what we've also noticed is that these supermassive black holes have been around for a long time. So we can look when we do these really deep telescope images, we look really far back in time. And what we see is evidence for these supermassive black holes very, very early in the universe. So basically, as galaxies are forming, we see indications of these supermassive black holes at the same times as galaxies are being created. So basically, as the galaxy grows, so does the supermassive black hole. And so it's not clear how we can get these supermassive black holes so quickly, so early in the formations of galaxies. And so there are a couple, there are a few ideas as to how that can happen. One is that, as a galaxy is being formed, you can start out with like some giant gas clouds near the center. And what can happen is these giant gas clouds, there can be so much self-gravity within these gas clouds that they can just collapse in on themselves, and they'll collapse directly into, very large black holes. And then these large black holes near the center of a galaxy will, attract each other through gravity and kind of merge and coalesce into one, basically supermassive black hole. Another idea is, basically another idea is that near the center of a galaxy, you can have some gas clouds, maybe not very, very large ones, but smaller gas clouds. Those collapse into stars, and some of these stars will be incredibly massive. And so they'll burn out very, very quickly because they have so much mass. They just burn through their fuel very, very quickly. And when they do that, then they'll go supernova, and then the remnants that's left behind will be what's known as a stellar mass black hole. And so these black holes are hundreds to thousands of times the mass of the sun, whereas supermassive black holes again are millions to billions of times the mass of the sun. So the idea is that perhaps these stellar mass black holes, these black holes that are formed from stars, that we create a ton of these near the center of a galaxy, and those all kind of merge together and then eventually form a supermassive black hole. So those are really the two main ideas, but we don't know which one is correct, and it could be neither one. We really don't know what the mechanism is that forms these supermassive black holes. So one thing that may help to figure that out is looking for galaxies that have what's known as an intermediate mass black hole in their center. And these are galaxies with black holes in their centers that are hundreds of thousands to 1 million times the mass of the sun. And we really don't see a lot of these. So as far as I know now in the literature, I think there are maybe a dozen cases that are potentially intermediate mass black holes, but I think there are only, maybe three that are confirmed. So we have very, very few examples of intermediate mass black holes. And so it would be interesting if we could find a lot of examples or more examples of galaxies with intermediate mass black holes, because this could tell us, what makes these galaxies different from every other galaxy. Why do they have an intermediate mass black hole and not a supermassive black hole? And by figuring out, what the conditions are that stopped these black holes from becoming supermassive, maybe that can tell us something about galaxy evolution and how these black holes actually grow. So it would be interesting to find a lot more cases of intermediate mass black holes so we can see what the common relationship is between them and what makes all of them different than basically every other galaxy. So one way to do that is by using a relationship that was published not too long ago, that was basically found out and published not too long ago. And so what people have found is that there seems to be a relationship between how tightly wound the spiral arms are in galaxies. So this is a parameter known as pitch angle. So the spiral arm winding is another term for it is pitch angle. So if it's really, really tight, if the arms are wound really tight, that's a low pitch angle. And if the arms are really loose, that's a high pitch angle. But what we see is that if the arms are wound really tight, that seems to correlate with a high black hole mass. And if the arms are really loose, that seems to correlate with a low black hole mass. And so when we look at this relationship, so this is just a cartoon of that relationship, but when we look at galaxies, we tend to find most galaxies up in this end of the relationship. This is where we tend to find most galaxies, and they all seem to have supermassive black holes. So what we want to do is we want to try to find galaxies that lie in the lower end there, where they have basically really open arms and potentially low black hole masses. So they may be intermediate mass black holes. And so we're hoping that maybe there's a way to find these galaxies to help us determine what's going on with their environments and what's maybe stifled their evolution. So we could do that. We could look at a bunch of galaxies. We could measure how tightly wrapped the arms are and then get an estimate for their black hole mass. Because images of galaxies are just everywhere. I mean, there are telescopes that take pictures of the sky, not directly at any individual galaxy. They'll just photograph a section of sky, move over, photograph another section of sky, move over, photograph another section of sky, and so on until they get the entire sky. And so these are called AllSky surveys. So obviously they're going to capture stars, they're going to capture nebulae, they're going to capture galaxies as well. But the thing is with these AllSky surveys is they're not tuned to look for any one thing. They're not tuned to look for, galaxies at a certain distance of a certain brightness, things like that. You're just kind of going with the luck of the draw. And so you can end up with galaxies like this in those surveys. And so you can see, if you look closely, you can see that this is actually a spiral galaxy. You can see that there's actually spiral structure in there, though the contrast is very, very low. So for instance, I can see there's a spiral arm right here, and there's a spiral arm right here. But the interarm region right here, the contrast is very, very low between the interarm region and the arm region. And so, for instance, if we were to use a computer program and just take these images of galaxies and just plug it in there and then measure the winding, the computer program would have a really hard time figuring out where the arms are. And so we can't really do it automatically, not with images like this. And so what we thought was that we thought we would use the ability that people have, like the tremendous ability that people have at pattern recognition. So basically, the human mind is great at recognizing patterns. Even in cases like where patterns don't exist, the human mind looks for patterns even when they don't exist sometimes. So people are great at finding patterns. So we thought we would take advantage of that, try to take advantage of that, and have people show us where the arms are. So that way we don't need the images. We could just use what people show us and measure that rather than use the actual image itself. And so this is just a little schematic showing you like the idea of the process. So instead of using the galaxy image itself, what we can do is show people the image, have people trace out where the arms are, where the brightest parts of the arms are, and then we can just throw away the image and just use the tracings that people leave behind and then measure those instead. And so we ran with that, and we created a project called Spiral Graph. So this is the citizen science project, and we've created it on the Zooniverse platform. So if you haven't gone to zooniverse.org before, you should really check it out, because there are tons of citizen science projects there. And I would say most of them have to do with pattern recognition. And that, there are history projects, there are biology projects, there are astronomy projects, there's all kinds of stuff. So like even the history projects are, transcribing documents, like really old documents, because, computers have a hard time deciphering people's handwriting, but people have an easier time seeing that. So people will read, other people's handwriting and then transcribe it and type it out. So that way, we have now a digital copy of it and can accurately understand what people have written in the past. So anyway, zooniverse.org has a ton of great projects, and this is on there. So the procedure to our project is actually pretty simple. So what we did was we took a large sample of galaxies, and we took galaxies that another citizen science project called Galaxy Zoo has, where people have already classified in that project all of these galaxies to be spiral galaxies. So they're very likely spiral galaxies to begin with. And so what we want to do is just show people these spiral galaxies and just have people trace out the arms. When we started this, we realized that some of the galaxies that people using Galaxy Zoo classified as spirals weren't actually spirals. So for instance, this image A down here, this is not a spiral galaxy. This is actually a merger of two galaxies. So what we had to do, we had to add a step in the beginning, asking people, is this a non-interacting spiral galaxy, or is this something else? Is this a merger? Is this an elliptical? Is this galaxy off center? Is this, are there problems with this image? And so what we do is we ask people, is this a smooth, merging, or otherwise somehow untraceable galaxy? Then select A. So this is, in this case, this image A here on the left is an example. Or is it structured, and is it a not merging galaxy? So does it have structure? Does it look like it's regular? Does it look like it's not merging with another galaxy? And if you select B, if you select, for instance, like this image, then what we do is we ask you to trace out the spiral structure that you see. And so this is a little GIF of somebody, tracing out some spiral structure in one of these spiral galaxies. And so we did that. So these are some preliminary results. So we did that with a sample of about 6,222 galaxies. And just based on the classification, so, are these non-merging spiral galaxies, or are these something else? Based on the Galaxy Zoo data, where people said that these were spiral galaxies, we found that about half of them, we couldn't convincingly say that these were non-merging spiral galaxies. So about 3,000 out of the 6,000, we weren't too sure about, or people weren't too sure about. So we aren't really going to try to measure these at all, because we're not convinced that these are, unperturbed spiral galaxies. But about 3,200 of them were actually people were pretty convinced that these were perfectly acceptable galaxies. So we do have a lot of galaxies in our first batch that we can actually measure. And so this is an example of, this is actually an early example of people tracing out the spiral structure of a spiral galaxy. So again, this is that first galaxy that I showed you with that's, the contrast is really, really low. And so you can see 15 different people agreed that the spiral structure can be traced. And you can see that they have pretty good agreement. Where it's really bright is where everybody agrees with their tracings. And so this is going to be much easier for our software to measure than, for instance, this galaxy here on the left, the galaxy image on the left. And this is actually a more recent image where we've kind of refined how we show the tracing details. But again, this is a different galaxy, and you can see the arms pretty well, but the brightness in the inter-arm regions here is still pretty high. So it's still hard for a computer to determine, where the arms are and where the arms aren't. But in this case, where people have traced out the spiral structure, this is incredibly good. This is all, as good as you can possibly get. And so we're able to measure this tracing image very, very accurately. So finally, what else can we get out of it? So not only can we measure the spiral, so we're able to measure the spiral structure from a ton of images, and from that we can estimate the mass of the supermassive black hole, or the mass of the black hole in the nucleus of the galaxy. But we also get different information. The spiral arm winding has also been shown to relate to the mass of the bulge in the center of a spiral galaxy. It also relates to the maximum velocity at which the spiral galaxy rotates, and that relates to the amount of dark matter that spiral galaxy contains. So all of these things are difficult to measure. You can use telescope time to measure all of these things, including the supermassive black hole mass, but it takes a lot of telescope time to be able to measure these things. Whereas if we use these images, these AllSky survey images that already exist, it takes almost no time to create, a good estimate of what these parameters are, and then maybe follow up on the interesting cases with telescope observations. And so that's one of the plans that we have. So one of the cool things, I think the coolest thing, is that we can actually get an estimate for the dark matter content of a galaxy as well. So I think that's pretty neat. But the other really cool thing that we plan to do in the future is, with all these people tracing these images and showing us where the spiral structure is in these images that aren't so great, we hope that we can develop a basically an artificial intelligence program that, based on that data, to have an artificial intelligence program show us where the spiral structure is in these poor quality images. And so what we can do is we can take the tracing images that people have produced, use some of those as a training set for the artificial intelligence program, and then train up the program so that way it can try to determine where the arms are in spiral galaxies. And then we have a whole other batch of data that we don't use as a training set that we can use as a check, and to see how accurate the artificial intelligence program is. And we can, refine it and keep refining it until it gets really, really accurate. And hopefully we won't even need people to do this anymore. Hopefully we can just have, the computer do it, and, much more accurately than computers can do it now. So that's a hope for the future. That's something that we're going to try to work on in the future. So, I mean, that's it. That's the citizen science project that I work on. So if you have questions about that, you can check it out. There's a link there, tinyurl.com/spiralgraph. If you go there, you can go directly to the project. There's a tutorial there. Chris Goforth, the host of this, also made a nice video tutorial. And if you go to the frequently asked questions page on my project, there's a link to that video tutorial as well, so you can watch that if you want. But yeah, basically it's all about looking at spiral galaxies and tracing out spiral structure. So hopefully you'll check it out. So if you have questions, I'm happy to answer them. I'm also happy to talk about anything else in astronomy as well. But yeah.
All right, we did have a few questions that came in while you were talking.
Sure.
And a lot of people right at the end there said, yay, Star Wars.
Yeah.
And you can see
yeah.
Nancy put a link to the event that's happening tonight for Astronomy Days, which Patrick's also involved in, which we'll be watching Empire Strikes Back and then have trivia time at the end. So check that out if you're interested. So the very first question I like to ask all people who do these citizen science live chats is, what do you get out of citizen scientists participating in this project? Like, how does it help you to use this approach versus any other approach you might use?
Well, I mean, like I said, I mean, people are so much, I mean, at this point now, people are much better than computers at pattern recognition. And, my collaborator and I, we could go through each one of these, 6,000 and this other batch of 14,000 galaxies, and we could do it ourselves and trace the spiral structure that we see in these images. But I mean, that would take us, months, if not years, to do. I mean, it's 20,000 galaxies. I mean, if we do one galaxy a minute, I mean, it's 20,000 minutes. So I can't do that math in my head, but it's a long time. But by getting people involved, and you don't have to be an expert. You just have to have, you just have to have an eye, you know, and I'd be able to, see patterns and things like that. And so, um, if we get people involved, and even if you do like one or two galaxies, I mean, that saves us already 1 or 2 minutes, right? And so we have now in the project, I think our registered volunteer count is up to 6,200 people, and people are cranking out, cranking out classifications in this thing. We're averaging about a thousand classifications per day. I mean, that's just remarkable. It's just a tremendous amount of time that's saving me, and you're contributing to a project, that hopefully will create some cool results. And then obviously, we're one of the goals too is like when we publish some of our data, the goal is to acknowledge all the volunteers as well. And so we're still figuring out how to do that, but there will be a way, at least in the acknowledgments, there'll be like a website link where you can look up your username and say, okay, this person contributed this much, things like that. So we're definitely gonna, the people helping out are definitely going to be acknowledged with this for sure.
Excellent. I know that's a big issue in the field of citizen science, how to recognize the people that are doing the work for you.
Right, exactly.
They are actually working for you in a way. So
right, exactly.
All right, we had a question way at the beginning when you started talking about are spiral galaxies the most common shape of galaxy?
So yes, actually they are. So it's this again, this is all estimates. So we look at a section of sky and we kind of count the number of spirals that we see, right? So in the local universe, so that being said, the local universe is nearby galaxies. So within, I don't know, hundreds of millions of light years. So in the local universe, spiral galaxies are the most common. So they make up, is estimated to make up about 70% of the galaxies that we see. And so the other galaxies are either ellipticals or what we call irregular galaxies, which are probably mergers, things like that. So weird shaped galaxies, probably due to mergers from other galaxies. But yeah, spirals make up about 70%. And then interestingly enough, barred spirals make up about 70% of that 70%. So barred spirals are actually the most common type of galaxy in the universe.
All right. We also had a question about elliptical galaxies. You said that there was a bright spot and then kind of not so much differentiation beyond that. And so the question was, is there just one star in that galaxy, or is it filled with stars still, but just has a bright spot in the middle?
Right. Yeah. So when you're looking at it, when you're looking at these elliptical galaxies, actually, maybe I can see if I can switch back and actually show you. Let me flip back to the beginning here and show you that elliptical galaxy. So really what you're looking at, when you look at all of these galaxies are so far away that you cannot see individual stars anymore. What you're looking at in these galaxies are just, billions of stars, so far away and so tiny that you can't see an individual star anymore. So for instance, this elliptical galaxy here on the left, these things here are stars within our own galaxy. These are galaxies in their own right. And this elliptical galaxy is just hundreds of billions of stars, just kind of spread out, all orbiting around a common center of mass. And so really what you're seeing here is, so the reason why it looks kind of yellowish orange is because these are all older stars, whereas these spiral galaxies have these bluer arms. So these are really hot young stars that dominate all the light here. But here, all those hot young stars are gone. And so you're just left with the older, cooler, redder stars here. And all of these stars, they're not orbiting in a plane. They're not kind of going around in a circular orbit. All of these stars are being scattered in random directions. So they get scattered out, and then gravity kind of takes a hold of it, and it comes back in and kind of goes through the center and scatters out in random directions. So that's why it looks kind of puffed up. And that's why it looks a little more concentrated in the center. but then it gets, it fades out as you get further and further away from the center, because those stars are, basically, some of these stars are being scattered way out, but not all of them. More of them are being scattered closer to the center, and so that's why you get that kind of distribution of light like that.
So I know you talked about the different types of spiral galaxies and had some classifications. So there was a question about which type of spiral galaxy the Milky Way is. Hopefully that's an easy question.
Yeah, that is not an easy question, actually.
Okay.
So the issue is that we cannot get outside of our own galaxy to see what it looks like. So it's hard to see, it's hard to know what our galaxy actually is, because we're in it. And we're in that plane, we're in that dusty plane of the Milky Way. And so we have to look through a bunch of dust through the disk to try to determine what it actually looks like. So that's actually more challenging than looking out of our galaxy at other galaxies and just seeing what they look like. And so one analogy I've heard that I really love is that it's like, so trying to map out our own galaxy is like trying to map out the streets in your neighborhood without leaving your house. So basically looking out your window and trying to be creative about how you can see what other streets are in your neighborhood without actually leaving your house. And so it's difficult. You just have to be creative, right? You need like good telescopes. Like for instance, using that house analogy, right? You have to look through other people's windows and see reflections off of teapots, to see out a corner window to see the street, right? You have to be creative about, you have to be creative about how to solve that problem. So with our own galaxy, I mean, looking at other galaxies, that gives us an indication of what to look for. Doing simulations of galaxies, showing us, how stars orbit, how gas and dust turns into stars, things like that. That all gives us an understanding of what to look for. And so from all that like theory and looking at other galaxies, the observations of other galaxies, we have an idea of what our galaxy looks like. But some of the evidence doesn't quite line up with our expectations. So we do know our galaxy is a disk, and so that's obvious. I mean, if you go out in a dark night, if you go out at night and look in a dark area, and you look up and you see the Milky Way, it's literally a band of light in the sky with like dark lines in it, right? And that's the dust blocking out the starlight. Now, if we lived in an elliptical galaxy, all that light would be basically evenly distributed around the sky. The fact that it's all in one band tells you that already that it's a disk-shaped galaxy, that it's some type of spiral galaxy. Now, we think it's a barred spiral galaxy, so there's evidence for that based on some of the orbits of stars. So some of that puffiness near the bulge. I think we have evidence that there's a bar. There's contradictory evidence because some people have determined that there are two bars about the same length, which we have never seen in another galaxy. But there's some evidence for that. So that's weird. We don't know how tightly wrapped the arms are. I mean, there's some evidence for that. People have measured it, but it's not clearly known because it's hard to map out the arms when you're in it. So it's a mystery. It's more of a mystery than other galaxies, in my opinion.
All right, that was an awesome answer. All right, we have a really technical question, which is how much slower relative to Earth time does time move for stars near the center of galaxies, like near that black hole?
Well, I mean, it depends. It depends on how close you get, right?
They specified 1,000 light years.
Oh man, okay. That's specific. I don't know. I mean, I don't know off the top of my head, but it does, I mean, it is general relativity, right? So these stars, so like, for instance, when we looked at that GIF of that, of just that field of stars orbiting around the unseen object, right? So those stars are actually moving pretty fast. I mean, that's taken over a period of years, but those are moving pretty fast. I think we've found in the not too distant past, I think we found a star that's moving, what is it, like at least half the speed of light or something like that. It's in orbit around the black hole at about half the speed of light or something like that. It's really, really fast. And so then relativistic effects really really start to take hold. Like, I mean, there's some measurable properties there when you're moving that fast already. I mean, it's still pretty slight, but it's measurable. I mean, you know, even like GPS satellites, right? I mean, they're orbiting around the Earth. The clocks in the GPS satellites are actually off compared to the clocks on Earth because of their motion around the sun and their distance away from the center of gravity and stuff. And so those always have to be recalibrated so that way you can accurately measure positions and stuff. So it really depends on how finely tuned you want to measure things and how close you are to like that black hole as well and how fast you're moving. So it's a combination of things. So I can't give you a number, but like if you put all that together, that you can measure the effects. Yeah.
All right, we had a question about wormholes and whether they can connect black holes, and if you think that is a possibility or not.
Well, so there's debate about wormholes. So what I've read is they are possible, but only on a quantum mechanical level, and in that they can pop into existence, and almost as quickly as they pop into existence, they pop out of existence. So it's really what I think it's known as like the quantum foam. So if you look at a really, really highly microscopic level, you look at the underlying kind of structure of space itself. There could be I mean, we can't find them, but it's theorized that that wormholes can pop into and out of existence, on very, very tiny scales. And so obviously science fiction has run with that and said, well, what if we made them bigger, right? And made them sustainable rather than like, immediately popping out of existence. What if we can make them stable and we pass through them? And then, yeah, obviously, yeah, then you can get some cool things happening. But there's people have actually also looked for kind of evidence of wormholes, and that like if matter or light falls into a black hole, perhaps that's actually the connection of a wormhole to an another point in space where all of that material exits. And so so on one end you may have a black hole, on the other end you may have what's known as a white hole. And people have looked for that, and those will have certain properties as well, but nobody's ever seen one. So far there's no evidence for any of those. So I would say it's very unlikely that they exist, especially on a large scale. But I mean, nothing is impossible, right?
All right, another specific question. Do you know which the largest star is and which the largest black hole are?
Oh man. Man, actually I just remembered, I think I just saw what the largest star was. Like, I can't remember the name of it, but there is a star that they've found that kind of defies theory, because you can mathematically kind of determine like how big a star can possibly be before it just basically it either collapses in on itself, or the material just kind of gets pushed away from the surface based on radiation. All the radiation pressure just kind of pushing the material off. And so there should be a theoretical limit to how big stars can be, and that the star was actually found to exceed that limit. And so it's not clear how that can happen, based on our understanding. Yeah, and the largest supermassive black hole, that keeps bouncing back and forth. Everybody always claims, like every so often there's a new claim that like, oh, this is the largest supermassive black hole, and this is bigger than anything we've ever seen. And then they kind of go back and look at the data, and they're like, nah, we measured that wrong. And so I don't know what the largest is so far, but it's definitely in the billions of solar masses. I think it could be like 6 billion or something like that. It's ridiculous. It's huge.
All right, we just got another question that's very the opposite end of this one. Is there a smallest galaxy that we know of?
Oh, smallest galaxy. Yeah, so there are. Yeah, so I mean, we have dwarf galaxies. I actually don't know what the lower limit for galaxies would actually be, because I guess a galaxy is defined as a gravitationally bound structure that's composed of stars, dust, and gas. but we've found like dwarf galaxies. So our own Milky Way is orbited by two dwarf galaxies, like the Large Magellanic Cloud and the Small Magellanic Cloud. And so we found dwarf galaxies orbiting around other galaxies. We find what we call low surface brightness galaxies. So they're basically they contain a lot of mass, but they don't contain a lot of stars. And so we think they're mostly composed of dark matter and very little normal matter, which is weird. So yeah, I mean, it's I don't actually know what the lower limit would be. The lower mass limit. It's hard to say. I mean, I don't think it's well defined. I don't think they've actually said, okay, this is the cutoff. This is now a cluster of stars rather than a galaxy. I don't know what the I don't actually know what the limit is. Yeah. It might actually be just, a physical size limit of, kiloparsecs. I don't know.
All right, so there's a question, since you brought up dark matter, about what dark matter actually is. If there's a way to explain that.
Right. Yeah.
Simply for us non-experts.
Right. Yeah. So we don't have a good explanation as to what it is yet. There are ideas as to what it is. But again, dark matter is something unique in that we know it exists because we can see its effects through gravity, but it doesn't behave like normal matter. So in that it doesn't radiate. So basically dark matter. So there are four fundamental forces in the universe. There's the electromagnetic force, the gravitational force, the strong nuclear force, and the weak nuclear force. And so we know that dark matter does not interact through the electromagnetic force, because it doesn't glow, it doesn't it doesn't radiate, it doesn't light. Basically, light does not interact with it. We do know that it interacts through gravity, through the gravitational force, because we can see those effects. We can see it bending light around it, like any other massive object. We can see it pulling on things. Stuff falls to the center of its mass, things like that. So we do see those effects. I don't know the reasons why, but it does not interact through the strong nuclear force, and it may interact through the weak nuclear force. And we're not sure about that, and that's where everybody's looking. And we're basically, scientists are hoping that it interacts through the weak nuclear force. And if it does, then there's a chance we'll understand what it is. Because if it only interacts through gravity and through no other of those four fundamental forces, then it's very likely we'll never know what it is. So there are a lot of experiments, deep in mountains around the world, that are looking for weakly interacting particles that could be dark matter particles, and so that interact through the weak nuclear force. And so there's some candidates, like there's one that I remember called the Axion particle, AXION, and I think that's a potential candidate for dark matter. I don't think we've discovered that yet. I don't think we found that yet. It's been predicted, but if we do find it, and if it exists in sufficient quantities, then it could be the dark matter particle. But again, it's not to say that it is. It's not to say that any of them could be. It could be it just interacts through gravity. It's just something that interacts through gravity, and we may never know what it is. And that makes up about 90% of the mass in the universe is dark matter. So that would be something if we never know what that is.
I'm kind of fascinated by those unknowable things, like the possibility exists that we will never know, and that I'm sure that's really frustrating to some people, and it really drives a lot of research. That nagging question that might never be answered.
Right. Yeah. I mean, that bothers me, that there could be things that we will never be able to know.
All right, we got a question earlier about if there are stars that exist outside of galaxies or other, clusters of objects.
Yeah, I mean, there are like rogue stars, but they generally are kind of get slingshotted out of galaxies. So you can't just really have a star forming outside, between galaxies on its own. That generally doesn't happen. But what can happen is, a star you could get like weird, basically lucky things can happen to a star, for instance, so like two stars could be in orbit around each other. For instance, one goes supernova, and that may like may slingshot this other star and give it enough velocity to actually escape the gravity of the galaxy, and it may, be kind of a rogue star then, just kind of flying outside of the galaxy on its own. So I mean, it's possible. There aren't many, and they're hard to see, but I think it is possible. Yeah.
All right, I've got one more kind of technical question before a more general question.
Sure.
We'll wrap up. So the more technical one is, how long does it take for a black hole to eat something like a planet or a star?
It could take almost no time at all. So I mean, that depends on the trajectory, right? So the star has to happen to, the star has to get close enough to the black hole to end up getting pulled into it, right? So basically, if it passes by a black hole, like kind of in a grazing manner, it could take a while for it to actually kind of spiral down and actually like fall into it. Or if it just happens to be on a collision course with it, it'll just drop right into it. So it's the same thing. Like if you go to these, if you go to some of these museums where they have those penny wells, where you drop a penny and it kind of just spirals into it, right? I mean, you can put it on that little chute and it'll just slowly spiral into the well and then finally drop in, or you could just take the penny and just throw it in yourself, right? You could just throw it straight in, and and end your misery quicker that way. So it really depends on the trajectory. But if it goes in slowly, weird things will happen. It'll basically get stretched apart, form a disk of material, and all that material will like heat up and really glow, and then it'll eventually fall. All that material will eventually fall into it. And that's pretty cool to see.
Or have you ever seen anyone just chuck a penny into one of those things without watching it do the whole spiral?
I've done that. I've done the spiral, and then I try to do it. I try to like just roll it in myself sometimes too. So I've done that. Yeah.
Excellent. All right, the last question I have for you before we wrap up, and if you're willing to answer a few more questions, I know we've got a couple other people that would like to ask you a few more, but the last main one I want to ask is one that was asked, which is, what is your favorite part of your job?
Oh man, I don't know. There's a lot of fun parts. I mean, I like talking about astronomy for sure. I mean, I'm glad. I'm always happy when people want to listen to me talk about astronomy, because it's always fun to talk about. So that's cool. I get to do that. I get to do that often, so that's neat. But I don't know. I mean, I like, honestly, a lot of astronomy is basically computer work. It's a lot of coding. And honestly, I like coding. I like writing computer code, and I find that to be fun. I mean, you can just sit down, put on some music and just, write code and try to analyze some data, and so you're basically building something to unlock the mysteries of the universe, basically, at your computer. So basically you're just building some code to unlock the data to show you, what's actually happening. And I find that to be really fun, especially when the code works, when you actually get it to run and it does it correctly. It's great, because then you're like, oh, look at that, I have data, I can make graphs, I can see what's happening. That's actually a lot of fun.
I'm so envious you have that ability. I am the world's worst coder. Just atrociously awful.
Oh, I'm not good. I'm not good. I mean, so my collaborator, he does a lot of coding. He basically builds most of this stuff. And so I feel bad whenever I code stuff and I show it to him, because I'm like, well, here's what I have. It works. And like, I see his code and it's just all clean and it works and it's like just precise. And I'm like, okay, well, mine's basically like one-time use code. Mine's not made for public consumption.
Well, if it works, then you're doing better than I would ever do. All right. Well, I think that about wraps up what we are trying to do here today. Thank you, everyone, so much for joining us. I'm glad you were able to listen in on something one of our awesome astronomers is doing at the museum. You should have a link to his project in the chat if you want to go back and actually participate in Spiralgraph. It's a really fun project. I find it to be kind of like what you're saying with your coding situation. Put on some music, a podcast, you can just click on galaxies and graph arms, which is really fun.
Yeah.
So please feel free to do that and contribute some data. And then don't forget, we do have the Star Wars viewing tonight if you would like to see Dr. Treuthardt do another thing.
Yeah. Chat about Star Wars. Chat
Yeah,
about Empire
Star Wars
Strikes
is
Back.
awesome. So,
Yeah.
all right. Well, thank you everyone so much. And if anyone has any last lingering questions they want to ask, we'll stick around for just a few more minutes. But thank you all so much for coming, and we're really excited to have you here today.
Thanks, everyone.